Okay, so this will be the last VASP, well, let's say the last VASP feature-related talk. I think afterwards we'll do something about a short little presentation or a summary about parallelization strategies in the program, which will help you to decide how to efficiently use the hardware here at NERSC. I think you will present something as well, right, Senji, in this respect, after the as a second talk, right?
Yeah, right.
Yeah. Okay. Cool. So I hope I'll stay in time. So 10:30, you said, right? Okay. Good. So today we'll discuss one of the more advanced features of the code, a beyond DFT technique, which in general we call the random phase approximation. We heard about it yesterday. This was one of these approximations in the description of dielectric properties. And when we discussed dielectric properties, I already mentioned that these the microscopic dielectric properties are input to some methods that go beyond density functional theory in the description of electronic correlation. And those two methods are GW and ACFDT. So GW for electronic structure and ACFDT for total energies within the random phase approximation to the dielectric screening. So yes, past is DFT the past? Well, DFT is still very much the workhorse of many projects in the present as well. So it has definitely have the most experience with DFT. At the moment, I think that many people use hybrid functionals on a more or less a day-to-day basis as well. And I think the immediate future, so the very near future, we'll see something very similar for the description of electronic properties in the random phase approximation as well. So there's many codes now that can do total energies and electronic structure in the random phase approximation, and efficient algorithms are emerging, and computers are getting more stronger all the time. So I think that what is true for hybrid functionals now will be sort of true for the random phase approximation tomorrow, which is a good thing because there is a need to go beyond density functional theory and hybrid functional theory. We already saw many of these things yesterday, or at least on the slides of yesterday. So in terms of total energy differences, atomization and formation energies, reaction barriers and things like this, we're definitely still not there. So we can't make predictions with sufficient accuracy from these levels of theory. For band structure, and well, here we always look at band gaps, but band structure is more than this, of course. But looking at band gaps, we see that hybrid functional theory does really well for a host of materials, small to medium gap size materials. But as you go to larger gap size materials, there's still large deviations with respect to experiment, and there's always difficult cases where even for the smaller gap size systems, hybrid functional theory is definitely insufficient. And van der Waals interactions, which is a definite thing that is becoming more and more important as people turn to molecules and molecular systems. Yes. So this is for instance one of those cases. I just put it there as a sort of a case study where we see the effect of I'll show the effect of including van der Waals interactions. So this is a reaction inside of a zeolite cage. So this is one of those things that people study in oil industry. This is one of the things that is important for cracking. And we see here there's a very complicated reaction path that has been studied by a colleague of mine. And so the difference between the drawn line, so there's all kinds of barriers in there, and the difference between the drawn line and the dashed line is that for the dashed line there were attempts made to include van der Waals interactions in these calculations. So there definitely have a large effect, and they're mostly not captured by density functional theory and hybrid functional theory at the moment. So having said that, there's still a very active development of density functional theory, which is good, and there's promising functionals emerging. These are definitely not the newest ones, so there's newer, very promising density functionals around. In this respect, I really like to mention the scan functional that has been implemented in the code as well, and will be definitely in the next update. And the scan functional is one of the density functionals. It's a meta-GGA, one of the density functionals that is able to capture partly capture van der Waals interaction. So, and a meta-GGA is a functional. So what we saw, how we saw functionals that depend locally on the density or a derivative of the density, but a meta-GGA depends on the second derivative of the density as well. Okay, so I won't go too much into these slides. You can have a look at your leisure at the publications that are quoted there. There's a thing such as van der Waals density functional theory, so non-local density functionals, and non-local in the sense that they have a kernel that depends on R and R prime, and it allows for interactions between densities at a point R with densities at a point R prime. So in that sense, the introduction of these van der Waals density functionals spawned a whole host of new functionals, and some of them work quite well in some situations, but there's definitely no universal van der Waals density functional at the moment. Okay, so this we saw yesterday. This with respect to hybrid functional theory. I made the point that that hybrid functions are definitely not general functionals at the moment. We combine a molecular system with a metallic surface. We see that in DFT we have problems describing these systems, which is the CO adsorption on D metal surfaces. We have problems describing these systems because DFT fails to correctly describe the CO electronic structure, and if we turn to hybrid functionals, we do better for the molecule, but worse for the surface, and overall agreement with the experiment is not good. And why do I show this again? Because I will show what kind of description we'll get in the random phase approximation. So I'll come back to this later. So from the point of view from a one electron picture, in DFT we have these Cohen-Sham equations that we solve, right? So we have a Hamiltonian that depends on a local potential. We saw this before. In hybrid functional theory, we have very similar looking equations, the Rotan equations, with a local part, Hartree part, external potential, and a non-local exchange potential, the Fock potential, that we solve. And now we go one level beyond, and it's still, the equations look very similar, but this object here, so we had a non-local potential here in hybrid functional theory, and now we see that this is not only non-local, but also energy dependent. And this object that we'll look at in the random phase approximation, and these are the GW quasi-particle equations. This object that we introduce here is called the self-energy. And so this is a level of complexity more, so not only non-local, but also energy dependent, and this energy is of course this quasi-particle energy that is partly a solution to our equation. So there's an additional level of self-consistency involved here as well. So we'll discuss this in terms of green functions, because the point that we'll make is that this self-energy in the GW approximation is the product of a Green's function and a screened Coulomb interaction. So let's have a look at what Green's functions actually are. So the Green's function, by definition, it's the inverse of the Hamiltonian. That is written here. And the nice thing is that for our Cohen-Sham system, for our non-interacting Hamiltonian, we can write the Green's function in terms of quantities that we can access, right? So we have here our Green's function as a sum over one electron orbitals that we get out of solving our Cohen-Sham equations and these one electron eigenenergies. So that's nice. We do know how to get the Green's function of a non-interacting system, of our Kohn-Sham system. Well, this is just a description of how you would arrive at a Green's function for an interacting Hamiltonian, starting from the non-interacting one, but I won't go deeper into that now. So what does the Green's function physically mean? So physically, the Green's function, and I've written it here explicitly in terms of time. You will see terms of arguments of time and arguments of frequency will frequently change within the formulas. That is simply a transformation from time domain to frequency domain, so basically plays the same role. So a Green's function, depending on r and r prime and on t and t prime, describes the propagation of a particle. So say I have a particle, an electron in this case, for instance, at point r at time t. So what is the chance of finding this particle at point r prime at time t prime? So, and in terms of time, this depends only on the difference between these times. So that is what the Green's function physically means. And it's often called, for that reason, it's often called a propagator, because it tells us how our particle, if it is at some point at a certain time, how it propagates, what the chance is of finding it, that it has propagated to another point at another time. So, well, this is a little shorthand for this. So 1 and 2 means R1 and T2 and R2 and T1. And if T2 is larger than T1, we call this a particle propagator, and it describes an electron. And we often write it in terms of diagrams, and I will sort of throw a few diagrams at you and hopefully make a case for the fact that they do elucidate this kind of theories and do not necessarily only obfuscate things. So we have a point 1 and a point 2, R1, T1, and a propagation from one point to the other in space-time. So this particular function, we can write it like this, where it depends on frequency, and here it is explicitly written in terms of in the time domain. Right. So that's a particle propagator if T2 is larger than T1. For the reverse, so and that's the reverse direction, if time were to be along this axis, for the reverse direction, it describes the propagation of a hole from point R2, T2 to R1, T1. Right. So, and there's a corresponding function, again in terms of our Kohn-Sham orbitals and Kohn-Sham eigenenergies related to this. So these lines that you will see in these diagrams are propagators of particles of electrons and holes. So the self-energy, in perturbation theory, the self-energy is a function of these Green's functions. We can write it as a function of these Green's functions. So, and what we see here, we can draw all these nice little diagrams, and I will sort of give some indication of what they mean. A little thing like this, a little ball like this, is just the density at a certain point. And this little wiggly line is a Coulomb interaction. So this is a particle traveling in my system, interacting with a density through a Coulomb interaction. So this is a simple Hartree interaction. Written like this here, and so this is called this is called the density bubble, I think. What you see here is called in Feynman diagrams, in terms of Feynman diagrams, is called an open oyster diagram, and this diagram represents exchange interaction. I'll show you how you can derive formulas even from these particles, from these diagrams for these elementary interactions, but I won't do that too much. I just want to go to these classes of diagrams because they are very important, because they constitute the random phase approximation. And they tell me I have a particle here that interacts with its environment through the Coulomb interaction, and what happens here, it creates an electron and a hole that travel to our system, And this kind of thing is we call a polarization bubble. So what does it do? It travels through the medium, it interacts with its surroundings and polarizes the medium. That is actually this little wiggle and such a polarization bubble. So it polarizes the medium, so it induces a change in the density, and that works back on our particle through the Coulomb interaction. But we could envision higher order processes in perturbation theory. So we have our electron as it travels happily through the medium, interacts with its surroundings, polarizes it. That polarization, that change in the density, works on the surroundings through the Coulomb interaction, induces a further change in the density, that then works back through the Coulomb interaction on our particle, and so on, and so on, and so on. So that we can sort of add these polarization bubbles ad infinitum here. So, and this whole class of interactions, together up to summed up to infinity, constitute the random phase approximation. So there's many other possible interactions, right? Exchange we'll take into account, but there's higher order exchange processes possible as well. So you can draw all kinds of complicated diagrams, but in the random phase approximation, the only interactions that we'll include in the description of our particle as it interacts with its surroundings are those guys, those what we call polarization bubbles. And why do we do this? So let's first, okay, maybe this is a little side issue. I said to you that this is a density. Well, actually, this shows you how to construct out of such a diagram, how you can construct a formula that is sort of human readable out of it. So I don't want to go into this too much. You can have a look at it if it's of interest to you later. But this shows you that this indeed is a Hartree interaction with the density, and yes, indeed, such a diagram constitutes an exchange interaction. Anyway, so why make this point of explaining these polarization bubbles in such detail? And that is because summing up the effects of all these interactions is easier than including the other interactions. So they're very important interactions, and we know of a convenient way of how to do this, actually, because including other ones is computationally very demanding, right? But this we can do more conveniently than including the other ones. So that's one of the things which makes the random phase approximation at the moment popular, not only because I'll show you that it's a fairly good approximation for the physics in many cases, but it's also a tractable one, right? So we can do it. Yes?
One more time understanding the polarization diagram.
Yes.
So what is it showing? Is it electron traveling?
Yes. So this is actually, yes, this is so I refrain from saying that this is the direction of time, because in these diagrams I violated that definition in the exchange-like ones. But for these ones you could say, yeah, this is time. So I have a particle coming in, interacting with the medium, creating an electron-hole pair that travel through the medium, recombine through an interaction with the environment, create a further electron-hole pair that travel through. So yes, in this sense, really, one direction is a propagation of an electron. The other direction, arrow drawn in the other direction, is the propagation of a hole. So yes, in that sense, it is there's a time in there, time and place, and all kinds of integrations, right? So yes, if you want to distill formulas out of it. So what is the nice thing about this random phase approximation is that we can express the sum, and not only of the polarization bubbles. So I include now explicitly exchange as well. So exchange in the sense of Fock exchange, that we can, this whole class, this whole sum, we can express as a screened Coulomb interaction. So, and this screened Coulomb interaction is now this doubly wiggled line. So we have this line, which is our propagator of our particle under consideration, And all of these guys, so this wiggly line and this wiggly line plus the bubble and the other wiggly line and this one and this part, we sum up and sort of put into this doubly wiggly line where we say this is our screened Coulomb interaction. And if we write that out in terms of a formula, this would be a bare Coulomb interaction. This would be a bare Coulomb interaction times an independent particle independent particle polarizability times a Coulomb interaction. And this one is V times chi naught times V times chi naught times V. And this is what we saw yesterday, right? So this is this thing that we can express as a geometrical series, and that in fact adds up to being our dielectric screening, right? So in the end, this is truly a screened Coulomb interaction. So that's how we end up from a description from a perturbative description of our self-energy, we end up with, well, W, this screened Coulomb interaction, times a propagator G. And that is why this method is called GW, because we have now cast our self-energy, the thing that we need for our quasi-particle equations, in terms of a propagator, in terms of a Green's function, and a product with a screened Coulomb interaction. Right. So that we have seen, so what goes in, that we have seen yesterday, right? This is our independent particle polarizability, which is in essence the change in the induced charge density due to a change in the, a change in the charge density due to a change in the effective potential in our Kohn-Sham system. And we can, as we saw yesterday, well, this formula looks a bit different, but we saw a very similar formula yesterday. This is just written in another way. We can compute this in terms of our Bloch orbitals, of our Kohn-Sham orbitals, and our Kohn-Sham eigenenergies. In this particular form, it scales with n to the power 4, as I told you yesterday. So this is a very computationally intensive step where we have a double sum. We have a double sum over orbitals. One is a sum over the occupied orbitals, and we have these empty states coming in, as I told you yesterday. But the nice thing is, and that I'll show you later on, that we can actually write this independent particle polarizability in terms of Green's functions as well, and end up with an algorithm that scales cubically. So in essence, scales as badly or as well as our DFT, with a very different prefactor though, but yes. So this is in its canonical form, it scales as n to the power 4, but if we cast it in Green's functions, we end up with a better scaling algorithm. That's a point that we'll come to later. So we've seen this is essentially what I showed you yesterday, right? So that we can write this sum as the product of our Coulomb operator and a geometrical series that represents the inverse of our dielectric matrix. Yes. So, yeah, then in essence we are set to do GW. We have an expression for our self-energy, the product of a Green's function and a screened Coulomb interaction. Well, it's written a bit more explicitly here. So what is a screened Coulomb interaction? It's essentially this thing where we have dielectric screening and 1 over r minus r prime in essence. And this is this Green's function that I already showed you yesterday. So compared to Fock exchange, actually you see that this is in essence a screened exchange interaction in GW. Right? If you make the comparison here, we have two orbitals n at r and r prime, and this is very much like the Fock potential. Only now the Coulomb operator in this potential has been screened with the dielectric properties of our material. And that is a connection that you could make, for instance, to hybrid functional theory, right? Because in hybrid functional theory, we say we use a quarter of this. Yeah, so this would be like using a fixed screening. So saying we screen this at every point r and r prime and every frequency with the same amount, with 1/4. And here we are, of course, we have an object that is material dependent, right? Because we compute this for every system. So it's not a fixed screening, but yeah, this tries to take into account the true dielectric properties of our system within an approximation. Right, so that's a recap of what we have seen before. So are there questions at this point? Yes?
So in random phase, what is that phase referring to?
That is a very good question, and I don't know. No, I really don't know. It's used everywhere, and I think there's even a lot of papers where they say we don't know where it comes from. And I don't know either. I have the feeling it comes out of high energy physics, an approximation that was used in high energy physics, but I couldn't say where. And it's a feeling I have that it comes out of high energy physics. Probably something that somebody at some point mentioned to me, but I really don't know why it's called random phase approximation. Yeah.
Essentially, when you create those electron hole pairs, you consider only a single excitation, right? So what would be the next level of complexity?
Well, the next level, what you would do here, actually, to go beyond the random phase approximation, we'll discuss this later, is to include exchange-like processes. Because by far worse than the thing that you mentioned is the fact that this is not properly antisymmetric. Yes, so you would have to but I'll come to this later. But this, for instance, as far as the exchange is concerned, there's only the naked exchange, this Fock exchange. So second order processes in exchange are immediately neglected already. So that's one thing that has serious consequences. And these guys, and there's a whole bunch of them that have little more wiggly lines here. They're called ladder diagrams. They're also neglected, and they represent excitonic effects. So that is one of the things that people commonly do to go beyond this kind of approximations, is include excitonic effects, and then you end up with something like beta sub beta equations. So yes, so if you create an electron and a hole, they don't feel each other's presence, right? In this case, as they travel, they should actually feel the fact that there's another guy with the opposite sign present. So that's all neglected. Yes.
So do you actually have the explicit naked exchange term, or does it just get added because of the?
No, that's added.
That's added explicitly.
Yes.
Okay.
Yes. Yeah.
When you're asking a question, can you stand up so that the ceiling mics can hear?
There's mics in the ceiling?
Yes.
Ah, Jesus. Okay. Yeah.
So can we use a similar idea to HSC to only apply to short range to reduce the cost?
That's what's done.
Well, yeah, the screening is in there, right? So
Okay.
yeah, but you wouldn't want to tinker with it because, I mean, and so the interaction is screened, but you wouldn't want to violate this anymore. Then you already have, because you computed in a certain approximation. But yeah, so the interaction is screened, but with the true dielectric properties of the well, not the true dielectric properties, but the random phase approximation to the dielectric properties of the material. Yeah. So no, you wouldn't want to play with that per se. So yeah, this is this analogy that I have alluded to already before. So there we do actually see the screening as a function. Well, this is the trace of this of this matrix with respect to reciprocal space vectors. And what we do see here, so it's for two materials, for a very small gap material like gallium arsenide, and for a material with a slightly larger gap, or with an appreciable gap like magnesium oxide. And you do see, especially for gallium arsenide, which belongs to this group of materials that is fairly well described by hybrid functionals, we see that the screening in this area, this red line, and this is an important area in terms of reciprocal space of the dielectric screening, we see that this fairly well matches with what the hybrid does for you. So this is an HSE hybrid. So it's not exactly 1/4, right? Because we have this error function, which of course means that we Fourier transform this. It's not simply 1/4, but we have a little variation. We see that this quite nicely matches. But if we go to materials with larger gaps like MgO, we see that the dielectric properties, if we would compute them in the random phase approximation, the onset of this screening here is quite a bit different from this 1/4 that we are effectively using. Right, yes?
Having problem understanding the x-axis, so G is the Green's function, or what?
No, sorry, G is a reciprocal space vector. Yeah, yes. Right, so as we go to larger reciprocal space vectors, we're dealing with faster fluctuations, yeah, in the response. Right, so we see that this 1/4 is actually a fair compromise for systems that have small gaps. So this is the reason why this works so well, these hybrid functionals. So this 1/4 doesn't exactly fall from the sky in that sense, right? It has some basis. Okay, so let me see. How am I doing? Okay. Yes. So I'll skip this because, well, this is a nice thing. This is an implementational point. How we compute the chi-naught in its using its spectral representation. This is computationally advantageous to do, and then you compute the imaginary part. You compute the spectral function, and then from this you get the imaginary part, and from a Kramers-Kronig transformation, or in this case a Hilbert transformation, you get the real part of the function as well. Anyway, this is just, I won't want to put too much emphasis on this because actually we have a better algorithm now to do this, and that will be released pretty soon. Okay, let's go to actually doing GW. Because we already said that I already said that this self-energy depends on this particular energy, right? On this quasi-particle energy. So there's a possibility to do an additional level of self-consistency here. These quasi-particle energies are given by this particular expectation value, and now we could solve this by iteration, obviously, right? So we solve this for starting with the eigenenergies of our Kohn-Sham system, solve the quasi-particle equation, get quasi-particle energies, put them in, solve it again, get new quasi-particle energies, put them in and solve them again, and so on, and so on, and so on. Right? So that is written here, and actually what we do, we linearize this equation around the quasi-particle energy, around the current quasi-particle energy, and solve an equation like this. Yeah. And if you do not do any self-consistency with respect to these energies, to these quasi-particle energies, you are doing what we call single-shot GW, G0, W0. So in essence, you calculate the DFT orbitals, get these Kohn-Sham orbitals and their eigenenergies, simply plug them in, so compute the Green's functions belonging to this, compute the screening properties belonging from these orbitals and eigenenergies, and compute your Coulomb interaction and your self-energy, and solve these equations one time, where here the self-energy depends on the eigenenergies, on our Kohn-Sham eigenenergies. So that is single-shot GW. And where we have linearized this equation, so we take variations of the self-energy around our current Cohen-Sham eigenenergies into account in a linear fashion. That is what is mentioned here. So that is single-shot GW. One step beyond this would be what is called GW naught, because these eigenenergies that we put into our self-energy, they go into the Green's function, right? Under the, into the, do I have this here? Yes. Yeah, so into the Green's function at this point, that is where they go. But of course, they also go into this Adler and Weiser formula for the screening, right? So we can distinguish between updating our Green's functions in terms of the eigenenergies. Do we want to transfer these quasi-particles that we get from single-shot GW? Do we want to put them into our new Green's function? Or do we also want to put them into our description of the screening, right? So, and the most commonly used approximation beyond single-shot GW is actually GW naught, where we do not update the eigenenergies with which we have computed the screening properties. We only update them in our Green's function, right? And the orbitals remain the same. They're still Cohen-Sham orbitals. And the quasi-particles that we get from single-shot GW are now used to compute a new Green's function. And that is what we call GW naught. And that you can repeat a few times. So you can loop over this a few times, so 3-4 times, and then mostly the quasi-particles you get out of these GW naught calculations have converged. And why do I mention this so explicitly? Because this is actually, within the random phase approximation, this is almost the only thing that you could do on top of G naught, W naught that makes any sense. All the other things, and I will show you some examples, all the other things might be helpful in some cases, but in most cases won't work very well. And that is because, actually, and I'll show you the examples of this, it is actually because there's cancellation of errors involved in using the random phase approximation and using eigenenergies and eigenstates from DFT. So you do get a very nice description of your dielectric screening in the random phase approximation as long as you use eigenenergies and eigenfunctions from DFT. If you start to update this, your description of screening properties will not improve in most cases. So there's limits, right? Because we do not have the true dielectric screening. We have an approximation to this, and that approximation actually works quite well as long as you stick to density functional, let's say PBE, eigenenergies and eigenfunctions. Yes?
So in this case, you don't update the sign, right? In the G.
I don't have what?
In the updating the G, you only update the.
Only update the eigenenergies.
You don't update the
No.
wave function. So why
Right.
is that?
Well, that is possible, so approximately possible, but even more expensive. And we'll get to this. And as soon as you start updating more and more and more, what will become apparent is the limitations of your random phase approximation. So you're not going to get a better description. You're not going to get better agreement with experiment. You're only going to get closer to the true random phase approximation result, and that will then show into its entirety the limitations of your random phase approximation. So this is, from a practical point of view, single-shot GW and GW naught, where, as you say, you actually only update the quasi-particle energies, not the orbitals. Those are the things that within the random phase approximation make sense. If not, you will have to, so if you want to go beyond this, you will have also to go beyond the random phase approximation in your description of dielectric screening, which will be costly, much more costly than, yeah, right. So, okay, well, this is a little flow chart. Yes?
Is it possible to say typically comparing DFT with true answer, where GW and where GW naught and where G naught W naught is.
I will show a little graph that shows you in terms of band gap. I will show you some comparison of
And in terms of excited states and well, yeah.
Yeah, that yes, in the sense, well, GW is yes, that would be truly exciting. Yes. Okay. So DFT ground state, yes. So what we do, well, we saw a few of these things before, where we'll discuss this yesterday. When speaking about the dielectric properties, we start with the ground state calculation. We do one exact diagonalization of the Hamiltonian afterwards using the ground state's wave functions to get high quality virtual states, unoccupied orbitals, and then we run our GW calculation. Either G naught W naught or GW naught, depending on what you'd like to do. Okay, so yes, so what does this yield, right? So here we have, unfortunately, I really should update this graph to include the hybrid functions as well. But here we have DFT, the blue dots, as we saw before, strongly underestimating band gaps for all materials. Then we have G naught W naught using these PBE states. Those are the white triangles. So moves nicely in the right direction, but we see still substantial deviations with respect to experiment. And then GW naught, only updating the eigenenergies inside of the Green's function, moves us quite a bit closer to experiment. We see here that there are still cases that are problematic. I think this is, well, zinc oxide should always be sort of the devil. Anyway, it must be in here somehow, somewhere. But we see that we do uniformly well. So for the hybrid functionals going through these larger gap systems, deviations were quite substantial, and here we do, well, sort of uniformly well. And we see that actually updating the eigenenergies in the Green's functions makes a lot of sense here. So updating the orbitals. So there is the possibility to update the orbitals. This is the self-consistent quasi-particle GW. And there's, well, this is a description of how this is done. This is approximately done. I won't go into the technicalities of this, only mention that it is possible to do it. And there's a little flow chart how to do it. So it's essentially the same thing that we've done before, but now there's a slightly different keyword here that specifies the algorithm to use there. It's much more expensive than the calculations we saw before. And actually, there in most cases, there's really either very little improvement over a GW naught, or there's a slight worsening of the comparison with respect to experiment. So, and this is still, as you see, this is still using the screening from DFT. So we have still not updated anything in the dielectric properties of our system. That is remains still firmly at the level of DFT, right? So what do we do here? We update now the Green's function in its entirety, right? So not only the eigenenergies, but also the orbitals. And we see that in most cases, there's actually quite little difference with respect to GW naught, as we saw before. Yes?
So in some sense, the quality of your GW naught performance, like in terms of how well it agrees with theoretical band gaps, sorry, experimental band gaps,
yes,
depends on your input quasi-particle energies and wave functions, right? Or orbitals.
yes,
Which come from regular DFT.
yes.
So if is it, I mean, have you ever observed that if you go to a higher level of theory, let's say in the hybrid functionals, in using those, how should I say, those energies and orbitals as input, does GW perform considerably better compared to just regular DFT?
No.
No?
No. No, that is, and that goes back to exactly the same point made before, that this combination of random phase approximation and DFT input matches well. Only when your system at the DFT level is really, really horribly described, it pays off to do something like an HSE, an hybrid functional calculation, and G naught W naught. So don't update anything there. Then you can do a single shot GW calculation on top of a. So for instance, if you have something that in DFT is a metal and definitely should not be, then it might pay off to start from a hybrid functional, but you wouldn't want to do anything beyond single shot GW on top of that. Yeah. Yes. Okay, so there are cases where updating the orbitals in the Green's function pays off or is even necessary. So there's two examples here. On the left, we see barium titanate, and that is GW naught versus self-consistent quasi-particle GW naught. We see there's hardly any difference between, mainly looking at the onset of the blue and the red lines, we see there's hardly any difference, but if we go to lanthanum aluminate, we see that including updating the orbitals in the Green's function actually makes an appreciable difference. So there's no real way actually to say beforehand whether that is the case, whether updating the quasi-particles in the Green's function will change a lot, but the cases where it is in fact so are very seldom. Yeah. So this is an example of it, but there's not so many as far as I know. Okay. So this goes then to fully self-consistent GWs, and then the thing that I have been telling you doesn't really pay off to do. And this is just to illustrate that, and fully self-consistent GW means that now we do everything, right? We update orbitals and eigenenergies everywhere, not only in the Green's function, but also in our description of the dielectric screening. And see and behold, not only is it a much more computationally intensive operation to do this, but we see that now we firmly move away from experiment and we start overestimating the gaps appreciably. And that is because now what we see in fact here is that if we use RPA orbitals and RPA eigenenergies, our description of the dielectric screening is not good. So it is good within the random phase approximation. So the random phase approximation in conjunction with DFT orbitals and eigenenergies works nicely, but if you go to full self-consistency, you see the limitations of this random phase approximation. Right. So what is one of the things what is missing? So one of the most important things that is what is missing is excitonic effects. I showed you these what is commonly called ladder diagrams. So there's ways to include it at this level. So to go beyond the random phase approximation, to a more fancy description of the dielectric screening. And then actually at full self-consistency, you move back towards experiment. So this is the random phase approximation where we, when we create electron and hole pairs, when these bubbles arise, they do not interact, these electron and hole pairs, as they themselves travel through the system. So in that sense, there's no electron-hole interaction as it's labeled here. There's no excitonic effects. We can include them, this is by means of the nanoquantum kernel, this work by Lucia Reining. Can include them in the screening, and then we move back from these white triangles back to experiment. But this unfortunately scales like something like n to the power 5, n to the power 6. So it is possible, but it's not really tractable, right? So it doesn't pay off to go to do anything self-consistent within the description of your dielectric properties. Not if you want to remain within the random phase approximation. So that point is made here in terms of dielectric constants, ion-clamped dielectric constants. You could have a look at it, but it nicely illustrates this point. Yeah. So that comes to what do we actually neglect in the random phase approximation, right? So second order exchange like things and beyond, obviously, and these ladder diagrams, of which there are infinitely many themselves, that in essence capture excitonic effects. So second order exchange like interactions, there's no simple physical interpretation of these processes, but normally you'd say that if you're not antisymmetric in all your interactions, you have a certain level of self-interaction in our self-energy. So in the RPA description of our self-energy, the electron interacts with itself, which should not be, obviously, and these particle hole diagrams or ladder diagrams, they capture electrostatic interaction between these electrons and holes that are created, and those are these excitonic effects. And another buzzword that you will often hear of is they are the so-called vertex corrections in W. Well, what they do is they remove self-screening. So there's an energetic contribution in the self-interaction, and our electron that travels through the system in RPA also screens itself, which is not correct, obviously. So those are the things that are neglected in the RPA, and that works well in connection with density functional theory, Kohn-Sham orbitals and eigenenergies, but not so well if we go beyond. So the best approaches that you could do now is G0, W0, or GW0, possibly self-consistent quasi-particle GW0 on top of density functional theory, orbitals and eigenenergies. Or if PBE or density functional theory is completely unreasonable for your system, you might do G0, W0 on top of a hybrid functional. And those are the two things that make sense to do within the random phase approximation. So we spoke about this yesterday. The potentials that one should use in connection with these calculations are the so-called these GW potentials, so the underscore GW Podcar files, because they are constructed in such a manner that we represent scattering properties up to energies high up into the excited state of the atomic system, and that is necessary to get high quality virtual states that we need for these methods that sum over virtual states. So, are there questions? At the moment? No?
So the previous figure, why you have dotted line over there, like left figure? So what are those dotted lines?
The dotted lines.
Yeah.
Okay, the drawn lines are the scattering properties, and the measure of the scattering properties is this logarithmic derivative. And those are plotted here. The dotted lines are for the pseudo atom, and the drawn lines are for the all electron problem. So if they match, we have constructed a pseudo potential that truly represents the scattering properties of the all electron problem, and they do match here close to within the valence regime. They match nicely. If you go higher up in the spectrum, they do not match anymore, and our pseudo potential doesn't describe the scattering properties of our atom very well anymore, and that is done better here. Yeah.
So why not always use the underlying GW podcasts?
You could, in fact, always use them.
Are they more expensive?
But they're slightly more expensive because we talked about this PAW formalism where we have these local functions. These need more local functions. So the cost is actually, it's not so much higher. So the cost of doing a ground state calculation with these and these will yield, well, very, very similar results, and it will be approximately as costly. And slightly more costly here. Some of them might be a bit harder. That could be. It could be that but that would definitely not be the case per se. But it could be that for some examples, to get them to match up to higher energies, the core had to be decreased or something. And creating these potentials is sort of playing with many, many parameters until you end up with something that is that looks nice in this sense and still reasonable in terms of the number of plane waves that you would need to use to represent the valence electrons. So it might be that cutoff energies are slightly different. Yeah, so in that sense, one of them might be more expensive than the other one, but it should be very, very similar. So if you use a project where so normally you would say you wouldn't switch potentials inside one project, right? So if you're planning to do GW and you're planning to use these, you would probably use the same potentials for your other calculations with which you want to compare. So that the energies are directly comparable. Yeah.
So your benchmarks were all fairly simple closed shell semiconductors. Can you comment on how GW does with more complex materials like transition metal oxides?
Well, transition metal oxides, it's mentioned actually here, and it's one of these things that so strongly localized states are still a problem for GW as well. So there definitely is a very big problem in DFT, as we know. So 3D states or 4F states, we know that they are not where they should be in DFT. But that is definitely still a problem within GW as well. Yeah.
Well, this is also related to RPA. There are also problems with atomization energies, correct?
Yes. Yeah. We'll come to this. Yeah. Yeah. Because that is actually the next topic on the agenda, and that is RPA total energies. Yeah. So yes.
I have one more question.
Yes.
So from the figure you have shown, it seems like GW or whatever you do with GW, it's always move the band gaps up. I mean,
compared to DFT, yes, and
yeah.
it should.
So in the case like when DFT does really well in predicting the band gap already, if you apply GW on top of it,
Yeah.
what's going to happen? It just stay on, good value, or it just keep going up?
Actually, there's no such thing as a case where I think there's no such thing as a case where DFT does very well in predicting the band gap.
Okay. So
It is, yes, it's systematically underestimated.
So it always helps them.
Yes.
If you were to compare HEC band gaps to GW band gaps, how do they correct? Isn't it true that HEC band gaps are usually larger?
No. So they're actually that is why I said I should put that on the slide. So HEC does well in this area, and compared to for instance G0 W0, HEC would do better in this area, and here it would quite strongly underestimate the band gaps. So in that sense, HEC band gaps are definitely not always larger or always smaller than GW band gaps. But here, definitely, if you wouldn't go to GW0, if you would stick to G0 W0, you wouldn't get as good band gaps in that area as you would get with a hybrid function. Yeah. Yes.
So what in terms of the cold band structure? If you look at some D bands below the Fermi level.
Yes. So that is very hard to say. I mean, they're too high up. I would still say in
both
Yes, yes.
And no real which one is better, HSC versus GW.
I wouldn't want to venture. Yes, I'm sure there's people that can answer this question, but I can't, unfortunately. Is there?
So we have a couple of questions online. One I think was very similar. Which areas does HSE outperform GW?
Well, in the sense that in terms of G naught W naught, for small gap systems, hybrid functionals often do better. If you then compare to GW naught, which is a slightly more expensive calculation, I would say they're on par. Yes.
And can I use a combination of GW with not GW?
Can you use a combination of GW with?
I suspect the question is referring to running a VASP run uses both methods, GW and
At the same time, I'm.
DFT and GW. To clarify.
Well, yes, you can do both. Well, you have to do a DFT calculation before you do a GW calculation. So you would have. I mean, maybe I misunderstand the question, but.
Hang on. A little more clarifications coming through.
Okay.
Such as for VO2, V use GW and O use DFT.
No.
No.
No, inside the same. No. There's no way to distinguish. No. So use one functional on part of the system and another functional on another part of it. That's not possible. No. Okay. So what we have seen before, right? We have looked at electronic structure. So we have looked at these one electron energies and quasi-particle energies, things like this. And all of these equations that we have seen, so Kohn-Sham equations, Rotan equations, quasi-particle equations. So for the Kohn-Sham equations and the Rotan equations, they're the variation of a total energy expression with respect to these one electron orbitals, right? So now we could ask ourselves, are these quasi-particle equations related to some total energy expression in the same sense? And actually they are. So there is something like an RPA total energy. Before we have seen RPA band structure, which was our GW, and these RPA total energies, they are computed in what is called ACFDT, or you can derive them in what is called ACFDT, the adiabatic connection fluctuation dissipation theorem. I won't go through any of these theorems or the proof. I'll just give you the result, and the resulting expression. Well, it's a kinetic energy. This RPA total energy is a kinetic energy that we simply compute from our orbitals, as we have seen before. A Hartree energy depending on the density, completely common. Then we have a Fock exchange energy computed with the density functional theory orbitals. So in that sense, it's different from a hybrid functional, where you have hybrid functional orbitals. But this is Fock energy evaluated with DFT orbitals, and interaction with the ions, obviously, and the correlation energy for which we now have an RPA expression. And what we see here again is that this depends on the quantities that we have seen before in GW as well, on this independent particle polarizability that we can compute from our DFT orbitals and eigenenergies. So evaluate, and this is the correlation energy within the random phase approximation, right? And naively evaluating this, or in a canonical form, using this Adler-Wieser formula, this scales as n to the power 4, not because evaluating this particular expression scales like that, but because computing the independent particle polarizability has this unfortunate scaling behavior with respect to system size. So in terms of diagrams, this is sort of trying to show you what this kind of expression, why this kind of expression is related to what we have seen in GW before, right? So this is actually if you would remove this particular line, this one that goes up. If you would remove that propagator and think of that one as a straight line here, as we saw before, then what you see there is actually GW. That is, again, then one of these propagators times a screened a Coulomb interaction. If we look at what this logarithm does, so we expand this logarithm, it's a Taylor expansion of it, then it's a sum of this one, and of this one, and those are related to our GW equations in the following sense. So our total energy we can derive as the derivative, so GW is the derivative of our RPA correlation energy with respect to the Green's function. Taking the derivative with respect to a Green's function in one of these bubbles means removing one of these lines. And if you then play this through, so if you take this expression in diagrams that we saw before for these RPA total energies, and you remove one line everywhere in these diagrams, you end up with exactly the same thing that we saw before. So there is this connection between the total energy in the random phase approximation and electronic structure in the random phase approximation. Right, so in the same or in a similar sense as there is a connection between electronic structure from your Kohn-Sham equations and your density functional theory total energy, right? So, okay, so how well does this work? It works quite well. These are all slides that try to make this point, that compare random phase. So computations for lattice constants in the random phase approximation with other methods, PBE, MP2, Hartree-Fock, things like this. I don't want to go into all these details. You can have a look at this as you please. One of the things that I would like to mention, and that is quite important, that in this RPA expression for the total energies, we see here, for instance, the comparison between an energy versus volume curve for graphite and diamond, and we see that that for instance in the random phase approximation we get the equilibrium volume and structure for graphite correct, which is quite an accomplishment because there's van der Waals interactions going on there. So that's already an indication that within this total energy expression we get a measure of van der Waals interactions, and not only do we get that correct, but also these atomization energies for diamond and graphite, they're roughly degenerate, and that is something that one finds in experiment as well. Yes. So if we then go to, okay, that is sort of making this point again. Yeah, another thing is that the behavior of the total energy with respect to the interlayer distance in graphite has the right character. So it should behave as 1 over the interlayer distance to the power 4 that we do get out of our random phase approximation calculations for the total energy. Well, going one step beyond this, you could look at noble gas solids. So they're actually only bound by van der Waals interactions, or primarily bound by van der Waals interactions, and compute C6 coefficients for these compounds. And we do see that we get really quite nice results compared to experiments. So now we have finally a functional that captures van der Waals interactions as well. Well, does quite well for heats of formation. The bad news is that looking at this, that if one looks closely to the numbers, one sees that, well, we have quite nice heats of formation, but chemical accuracy is not reached for this particular functional, right? So we do quite well for many aspects, but it's definitely not the end of the line. Yeah? I've put this on the slide. We would like to be able to compute total energy differences with deviations with respect to experiment no larger than 1 kcal per mole, and that is something that is definitely not reached by computing total energies within the random phase approximation. The other thing that I already said that I would come back to this point is this CO adsorption on D metallic surfaces. And so this was one of those things that were hard to get right, that we didn't get right in DFT, that we didn't get right in using hybrid functionals. And so another way of looking at these problems is depicted in this graph. So what we see here is adsorption energy of CO on these surfaces, on 111 platinum and rhodium 111. And in the same graph, we've sort of plotted it against the surface energy. And what we do see, well, experiment is here, right? So, and we see that that for a whole host of functionals, and not only actually density functionals, but hybrid functionals as well, they move along these lines, and they combine two large absorption energies with two small surface energies. And that is actually a bit of a strange thing if you think about it. So intuitively you wouldn't expect this, because the too small surface energy means that the surface is actually a bit too happy to be a surface, and then it should not be so keen on binding anything. So these are the sort of two things that you wouldn't necessarily expect to occur at the same time. And not only this, but going from one functional to another, we see a sort of a trade-off between those two effects, and we move along these lines that doesn't get closer to experiment actually. If we do this in the random phase approximation, we move away from these lines and break with this, and for some stuff get actually quite close to experiment. And the fact that for platinum we're still ways off with respect to the experiment in terms of the surface energy, we partly blame the experiment for this. So, so we would like to blame the experiment for this. It's not so easy to do good experiments to get really reliable experimental data on these surface energies. So there's possibly room for improvement at the experimental side as well. Anyway, so recapping. Connecting to what we compared to before for this kind of systems, we have looked at site preference and adsorption energies, and now we see that not only do we get good structural properties, so we get very reasonable surface energies, we get good structural description of the system, but we also get good absorption energies now, and we get the right site preference, and that is sort of collected in this graph. That is a bit of a horrible graph. Anyway, this shows you that we are inside of, so this is experimental error bars. This is indicating that we are, this indicates where experiment says it should adsorb. And actually we do find the right sites, and we are within the experimental error bars for the absorption energies. So which is quite nice. And as we, so what we have is actually a total energy functional that sort of does well for the molecule, but also gives very reasonable results for metallic systems at the same time. And now we can really fully describe this problem. Before we saw that we do either well for the molecule with a hybrid functional, but screw up the description of our metallic system, or vice versa. We have a good description of our metallic system in density functional theory, but not of our molecular states. And this is reached here, so this is sort of unified here and works quite well. So that point is made actually here. So what do we see in density functional theory? We see that our molecular states are, HOMO-LUMO gap is too small, so this is where experiment claims it should be. or where it should be experimentally. Well, we're ways off, and especially this LUMO is much too close to the metallic states. If we go to the hybrid functional, we do very well actually for these molecular states, very close to where experiment would like them to be, but the d metal bandwidth has become too large, and especially in this area, the back bonding is still too strong. So if we go now to a GW description of this, which is this electronic structure pendant to our total energy, we see that especially for the LUMO, we still do very well. For the metal, there's almost no difference between density functional theory and the GW description. Homostates are not so nicely described, but for this problem, not of the main importance. And so this sort of unifies a good description of our LUMO states with a good description of our metal surface. Right, so to do GW calculations, RPA total energy calculations, there's a flow chart involved, a few steps. So there's an additional step compared to GW. There's a script in one of the, so for the hands-on section, there's a script that takes care of this. And have a look at all these scripts, because they simply, mostly they copy INCAR files to, so INCAR files to, an INCAR file that pertains to a particular step is copied to INCAR and then VASP is run. So, and then if you look into these INCAR files, you'll see all these tags, and hopefully the manual will be explanative enough to give you an inkling of what is happening. So what do you need to test in these cases? Well, the usual things. Well, this is something that we can probably discuss better at during the hands-on sessions. So what we do have is a well-balanced total energy expression that captures all types of bonding. What we unfortunately do not have is a total energy expression that is accurate enough to reach the final goal, which is this chemical accuracy. So I would like to mention this because I've alluded to it a few times and mentioned the fact that the way that we compute the independent particle polarizability scales so horribly with the fourth power of system size. Well, there's now we have been working on an algorithm that scales cubically, and so that removes this limitation. It's work of Mersu Kaltak, Jiří Klimes, and Georg Kresse, my boss. Well, this is again what we have seen, our Green's function. Now it's written in imaginary time, and in terms of a Green's function in imaginary time, we can compute the polarizability as a product of two Green's functions. And this is a point-by-point product, so over R and R prime. So what is the nice thing about this? A point-by-point product over two quantities that scale with system size scales as the square of the system size and not n to the power 4. So getting the independent particle polarizability this way is much, much cheaper. Yeah, well, you have to do some clever stuff to have a cosine transform of this guy to imaginary frequency, and then you can simply use it in this equation that now is the worst scaling step because there's a diagonalization involved of a matrix, and that scales cubically. So you end up with an algorithm that is not scaling as n to the power of 4, but n to the power 3. As in fact, yes?
Why do you have to diagonalize the last equation?
To take the logarithm.
Oh, you can take the logarithm of the determinant since you have the trace, so you don't have to diagonalize.
Really?
I mean, the trace of the logarithm is the logarithm of the determinant, right?
Yeah, but how would you?
Trace is the character of the matrix.
Right.
So instead of calculating,
Okay, you don't have to diagonalize.
instead of diagonalizing, you calculate the determinant of the matrix.
And that's what, and that would scale as?
Well, it's cubic.
Yes.
But it's not diagonalization.
Okay, yeah, okay, but we diagonalize here. So yes, okay. But would there be, would that be computationally attractive?
I think so, yeah. Instead of diagonalizing, maybe
Okay.
scaling better.
Okay, yeah, I should look into it.
Thermal
Yeah.
parallel scaling.
Okay. Okay, yeah, should look into this. Yes, because we use it to take the logarithm. We diagonalize it. Yeah, if that would scale better with respect to, for instance, processors or something like this. Yes. Okay.
Or memory as well.
Yeah.
So you don't have to store eigenvectors.
Yeah, okay. Well, in terms of memory, because that would be my next point, this is the limiting step, that we store these Green's functions. So actually, these matrices that we then diagonalize are definitely not our memory problem. But if this would scale better with respect to, if it would parallelize better, it would be.
The determinant using Cholesky decomposition.
Mm-hmm.
That is, from an algorithm point of view, better than
Yeah.
the diagonal.
Yeah. 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 Okay, good, thanks. Yeah. Yes. Well, anyway, that is the new algorithm. One of the critical steps is finding clever grids to do these transformations, and that has been done. This nice work of Mersu Kaltak, if you're interested. So we do need only very few points for these transformations, and that is more or less constant. So that doesn't doesn't change with system size. And yes, so what can we do this way? So prefactors are much larger than in DFT, is mentioned here, but we can do these calculations to systems like a few hundreds of atoms within, well, in this case on 128 cores in something like 300 seconds. So that's really quite powerful. The thing that hurts us the most at the moment is having to store the Green's function with respect to two spatial points, or with respect to two indices, and so this is very memory intensive. Yes, that's the current limitation. Okay, I think in the interest of time, we'll do questions and.
So we do have a question from online. Up to which order of interactions is included, has been included in the RPA total energy expression?
So in terms of these polarizability bubbles, up to infinite order.
Right.
Yes. But only in that sense, right? So only that class of diagrams is included, right? And the only other diagram that's included is Fock exchange using the PBE orbitals. Yeah. Okay. Any more?
So how does the GW response function compare to time-dependent DFT response function?
The GW response function.
The RP response function, the Kali?
Right. I don't know. So time-dependent Hartree-Fock or time-dependent DFT, or?
Yeah.
I mean, it should be the same thing, right? Yes, I would say it would be the same thing.
So there is no advantage in using that over GW RPA?
Well, we've spoken about this. So I think I know why you ask, right? So if you would want to excite your system and follow its state explicitly in time, you couldn't use this, obviously, right? But if you then from this response to get something like a frequency-dependent response function, then you could do this. But if you would want to follow your state as it decays in time explicitly, that is.
That's all the advantage, right?
Yes, I would say so. Yes. Yeah. Yes.
So, if I understood well, the dielectric response is calculated in a sum over state fashion.
Yes.
Do do you think that if you consider also the DFT level, the relaxation of the eigenvectors, the eigenfunctions, and so include this in the APA approximation, this would give better results? Do you know something about
So what exactly do you mean by relaxation of the?
Because against, say, you can have the sum over state approach for calculating the dielectric response, but there is this coupled perturbed approach which allows you relax your orbit, your eigenstates while you're in a self-consistent way. So you can calculate dielectric response properties, also taking into account the effect of the electric field on your eigenstates.
Okay, so you.
And this should improve the dielectric response evaluation.
Okay.
I don't know. If you have some coupling between these two methods.
I must admit I don't rightly know the method you speak of, so
Okay.
so maybe you could give me, is there something I could read on this, or
Yes,
I might be able to give you an answer, but right now I couldn't answer, sorry, yeah.
We have another one online. What's the difference between li_sv_GW and li_sv? Particularly, can I use the _GW to do only DFT?
Yes. So what is the difference? The difference is that one was constructed explicitly to reproduce scattering properties at higher energies as well. The other one was not. So for the ground state, there shouldn't actually be a huge difference. And there shouldn't really be an advantage of using one or the other for ground state calculation. Yep. So it's not that there's a trade-off that the scattering properties at high energies are now well described at the cost of describing scattering properties in the area, in the energy area where that is of importance for your ground state. So it should be equally well as before, right? Yeah. I think we're in time, Senji.